This is section 2.1, day 2. So you should have your notes out in front of you and be viewing this on your iPad, so the note technology is not really applicable. So let's just revisit from yesterday, day 1, what does a limit do? Remember that you had a reading activity where it had you find the answer to that question. And remember that limits, they give us a language for describing how the outputs or the y values of a function behave as the inputs or the x values approach some particular value. So it gives us a language. That language describes outputs, that's what the limit is, as we approach a certain input. So one of the approaches, if you remember from yesterday, we gave you 3 strategies. We gave you a plug it in, an algebraic strategy, and a trig strategy. And so this is the 4th strategy, and it's called the sandwich theorem. So the idea is that if we want to know something about function h, if we want to know something about function f, and we know that f is between g and h, if we can determine that g and h approach the same limit L, then since f is in between them, it should also approach the same limit L. So let's take a look at this phenomenon. For instance, here's a relatively complicated expression, x squared sine of 1 over x. And you have a graph of it. And so we want to know what's happening to those output values, those y values, as we approach 0. So if we want to get this on our window, our graphing calculator, let's have a window of, we're really zooming in here. We're going to go from negative 0.2 to positive 0.2 for the domain. And then we're going to go from negative 0.02, it's 2/100ths, to positive 0.02 for the y values, the range, and the scale is 0.01. And so that looks like this. Like I said, we're really zoomed in here. So if we look at this, we can visually, because we can use graphing as the way to evaluate a limit, we can see that graphically as we approach 0, this value should approach 0. So how do you then approach this analytically? And so the way we approach this analytically to kind of prove that it's in fact 0 is we take a look at this graph and we say, well, let's take a look at what's going on for bigger values and for smaller values in terms of the function values. So if we look at the tops of all of these hills and we kind of connect the dots, the tops of all of those hills kind of follow this x squared pattern. And that shouldn't be too surprising because we can actually see that is part of the function. So when we look at this function, we can see kind of an x squared and then some sort of oscillation. And then if we look below for values smaller, y values smaller, we can see that that follows a pattern of minus x squared. And so we're going to call this the bigger function and this the smaller function. And so let's take a look at these limits. So I'm going to go ahead and graph those right on my graphing calculator. And so I'm trapping this function that we want to know something about between 2 other functions that I know a lot about. And I'm pretty sure you're familiar with x squared and even minus x squared. I think you can kind of grasp that as well. So when I graph that on my calculator, it looks like that. So let's take a look at the limit of this smaller one and the limit of this bigger one. So what is the limit of negative x squared? Maybe I should have put that in brackets. As x approaches 0. We could just plug that in. We know that approaches 0, and we can see that visually on the graph as well. That it approaches 0 from the left and the right. Likewise, what is the limit of positive x squared as we approach 0? And we can plug that directly in too, or we can look at it in the graph. As we approach from both sides, it also approaches 0. So we know that this function, negative x squared, that's the blue one, that's smaller than our function for every value of x. And in addition, the red function, the x squared, is bigger than our function, bigger than or equal to our function for every value of x. So if these two functions' limits both approach the same value, 0, then this, we can conclude that the limit of this also approaches the value of 0. And we, like I mentioned before, we call this the sandwich or the squeeze theorem. This is another name that we also call it, because it literally sandwiches the function that we want to know about, this oscillating function, between two functions we already know. So before we jump into evaluating more limits, I just want to make a quick comment about fractions. And so, for instance, so when we look at fractions, we've got a numerator and a denominator. And I want to look at, situations where we can look at something and call it 0, or look at something and call it infinity. So, for instance, if we have 1 over a really big number, so 10's pretty big, 100's even bigger, 100,000's even bigger. If we go really big, we can, we know that the bigger we make the denominator, the smaller we make the number overall. We can essentially call that 0, okay? 1 over a really big number is 0. And contrary to this sort of philosophy, if we take 1 over a really small number, so, 1/100th, 1/100,000th, we can 1 over something that's really close to 0, we can essentially call that infinite. We know that number, this fraction, gets bigger the smaller we make, the closer to 0 we make this denominator. So those are definitely acceptable things to conclude when we're evaluating limits. Likewise, when we have 0 over any number, doesn't matter what the number is, it's 0. And any number over 0, doesn't matter what those numbers are, is undefined or infinity. So again, we can make logical conclusions about these scenarios. And so we're going to just kind of try to gain a level of comfort when dealing with those ratios and being able to determine limits. However, if we ever get 0 over 0, notice none of these are 0 over 0. But if we do get a 0 over 0, and we got that yesterday when we were evaluating limits, that's when we need to start trying other strategies. So if we try plugging it in and we get 0 over 0, you might want to try something algebraic or trigonometric, that sort of thing like we did yesterday. That's the real kind of stick in the mud here, is when we get this 0 over 0 scenario. So just a quick summary. Let's go over those strategies again. We've got our plug it in strategy. We've got our factor strategy. We have our trig identity strategy. We can always graph it if we're allowed to use a graphic calculator, but the times that we're not allowed to graph it, we're really going to have to rely on these strategies. And we also have the sandwich theorem that we could also try if we wanted to. So let's take a look at a couple of these. Can we find the limit? Okay, let's try with this one. Now, typically what we do is let me let that disappear. We try plugging it in first, and we try that visually. If I put 7 here and 7 here, I get 0 over 0. So plugging it in isn't going to work. So we should be able to recognize that if I have a ratio and it's polynomial, that I should be looking to factor. And the top can factor. So we had this scenario yesterday where when we factored the top, we had a set of factors on the top and the bottom that cancel. Remember, this is going to end up being a line with a hole at 7. Okay, because we know that when we have canceling factors, we have holes in graphs. So this line is going to look like this. It's going to have an intercept of 7 and a slope of 1. And it's going to have a hole at 7. Okay, and so now that we've canceled out the factors, we can we can now re-express this. Now plugging in 7 is okay. So notice that the first strategy we did was a factor. The second strategy now with the new expression is to plug it in. And so we know that the limit is 14. So let's take a look at number 2. Again, visually, if I put pi here and pi here, we're going to get 0 over 0. Okay, and 0 over 0 is that problem where we need to find another strategy. So we're going to use a trig identity. So we're going to take tan x and call it sine over cosine. And then I'm going to rearrange that. Instead of dividing by sine over cosine, I'm going to multiply by cosine over sine. The sines cancel. And so I'm left with the limit as x approaches pi of 4 cosine pi. And now I can plug in the pi. So I started out with a trig identity, and now I'm going to notice that last step is usually plug it in. And so when I plug in pi, cosine of pi is -1. So the limit here is -4. Okay, so let's take a look at this one. Plugging in 0 just visually gives me 0 over 0, so plugging it in isn't going to work. So I'm going to re-express this as sine x times sine cubed x. That allows me to create a sine of x over x ratio. So I'm going to rewrite that as its own ratio. We know that the limit as x approaches 0 of sine of x over x is 1. So now we're going to plug in 0 here. That's okay. And sine of 0 cubed is 0. So 1 times 0 is 0. So we know that this limit is 0. Okay, so this last one. Plugging in 0 at the top and 0 at the bottom gives us 0 over 0. So we know plugging it in is not going to work. Nor factoring. Factoring is not going to work. And we can't re-express this to get a sine of x over x either. So we're going to have to graph this one. There's no other alternative at this point. So let's go ahead and get your graphing calculator. I want you to set up a window from -5 to 5 and -2 to 2 for each of the x and the y directions. Make sure that you're in radian mode. And go ahead and pause the video now and get that set up on your graphing calculator, and we'll look at it in just a second. Okay, so, I guess I don't even have a graph of it. So looking at the window, looking at the graph itself, when x is approaching 0, we should be approaching something between 1 and 2. And so if you would go to the table and look at that decimal matches up with 7/5. So for reasons that I'm not going to go into right now, if you notice, this limit ends up being a ratio of this coefficient inside the sine function and this coefficient, and the denominator 7 over 5. And that will always be the case. And we're gonna spend a lot of time away from thinking about this. In fact, we won't even look at this until almost the end of the year again. But this will always be a graph it sort of question until then. Okay, so what did we accomplish? Well, we accomplished reviewing the methods for determining limits. We can graph it, we can plug it in, we can use algebra, and we can use some trig identities, or we can try to use sine of x over x. Okay, the pitfalls is that, excuse me, is recognizing when you can't plug it in. Okay, that's the big, so you must not forget to do some of these other strategies. Okay, so at this point you should be ready to do day 2 of the homework in WebAssign, and again, you got to get that to 100%. That doesn't mean doing all the problems, but because they are weighted, but you got to get that score to 100%. If you want to try the proficiency quiz and test out of these 2 homework assignments, you can. Remember that you have to get a score of 3 or 4 on the proficiency quiz the first time you take it in order for it to count. So if you try the proficiency quiz and you get a 1 or a 2, then just go back and do the WebAssigns to get your credit for completing the proficiency for the homework for section 2-1.